Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'll be going over how to find the percent ionization of a weak acid. So basically, to find the percent ionization, you need to know how much of it ionizes, how much HCl, or I'm sorry, H3O plus is formed, and then you're going to divide that by the original amount or concentration of your acid, and then you're going to multiply that by 100 to get the percent ionization. So you got to do your ice table again. So you got to find out how much change occurs, get the equilibrium expressions, plug that into your Ka expression, and find X. So the first thing you need to do is have a balanced equation. If you don't have a balanced equation, you need to make a balanced equation. So here you have HNO2, and you're looking to see how the acid is reacting with water. So you have a reaction with water with your acid. HNO2 aqueous plus liquid water gives you H3O plus aqueous plus NO2 minus for nitrous acid. So first thing you need to do is get the initial concentrations, the change, and equilibrium using your ice table. So we start with 2.5 molar. So we're going to have 2.5 molar. Let's see if I got the number of significant figures right. Yeah. So 2.5 molar. Here, water we're going to ignore because it's liquid. It's not going to find its way into the equilibrium expression because the concentration of water doesn't change, or of liquids and solids don't change. So we're going to ignore water, and here for the product, initially it's 0. Or very, very close to 0, so we're just going to put 0. So 0 here and 0 here. And then the change is going to be, since we don't have any products, the shift is this way towards products. So that means we're going to lose some of our reactant. And it's a 1-to-1 to 1-to-1 stoichiometric ratio. So we're just going to have minus X here. That means we're going to gain X amount here because it's a 1-to-1 ratio, as well as here. Okay, and then all we do is we add these together, and so this becomes 2.5 minus X, and this is still plus X and plus X. And so now all we have to do is plug this into our expression for Ka. So here, Ka is equal to, what's the Ka value for nitrous acid? That would be 4.6 times 10 to the negative 4. So we have 4.6 times 10 to the negative 4. And the expression, that's going to be equal to the concentrations of the products over reactants. So it's H3O plus concentration multiplied by the concentration of NO2 minus all over the concentration of the acid HNO2. And then so we plug the values in here, our expressions. So X for both of these, so it's X times X is X squared, so it's X squared over the expression for the acid, which is 2.5 minus X. And so at this point we can do the X is too small approximation, which basically is, again, we're assuming that this acid doesn't really dissociate all that much, such that the amount that does dissociate is negligible. So that way, even if we subtract out that certain amount from 2.5, it's still practically 2.5. So we'll do the x is too small approximation, and that simplifies our equation here. So then, again, this is equal to 4.6 times 10 to the negative 4. And so all I need to do is multiply both sides by 2.5, square root each side, and then you've got x. And in that case, x would equal 0.034. So x is 0.034. And then to find the percent ionization, all I need to do is take x, which is the amount of H3O plus formed, divided by 2.5, the original amount of the acid, and multiply by 100. So you take 0.034 divided by 2.5 times 100. Yeah, let's see here. Okay, and so we get, what's the answer? Okay, 1.4% ionization. 1.4% ionization. Okay, so you want to double check to make sure that this is a valid assumption to make with regard to the x is too small. Most likely is going to be valid, because if you look at the initial concentration and you look at the Ka value, this is 2.5 times 10 to the 0. This is 4.6 times 10 to the negative 4. That's a factor difference of 4 in the exponent, right? So that's most likely going to be a valid assumption to make with regard to the x is too small approximation. But again, you want to use the 5% rule to make sure. And again, the 5% rule is this here. So the calculation would be, you take your x value divided by the original amount, you multiply by 100, and you get 1.4, which is the same number as the percentage. So this is less than 5%, so it's a valid reason. Let's see here. Okay, so what about the second problem? So the second problem, we have 0.250 molar acetic acid solution. So basically we're going to do the exact same thing. So the first thing you want to do is have a balanced equation. If one isn't given to you, then you have to set it up yourself, right? So you have to know that in the acetic acid in solution is reacting with the water. It's going to give a proton to the water to form your hydronium ion, and what's left over is the anion, the acetate ion there. Okay, so you'll see that this is a 1:1:1 ratio. First thing you want to do is write out your ice chart. So the initial concentrations, you're going to start with 0.250 molar concentration of your acetic acid. And then we're going to look at here. So we have lots and lots of water. This is happening in water. So we're going to ignore water because there's so much of it. And of course, the concentration doesn't change as well. So originally, to start, we have a practically zero amounts of those products. Our hydronium is going to be 0, and our anion is going to be 0. So what about the change? Again, since we have no product, the shift is going to go in this direction. So we're going to lose some of our acid by a certain amount, x, and it's 1x because everything is coefficient of 1. So if we're going to lose 1x here, then we're going to gain x here, and we're going to gain x here because of the 1:1:1 ratio. and plus we're going in this direction. So we're going to gain some product here. So whatever we lose, we're going to gain the same amount over here. And now to get the equilibrium expressions, again, you add everything together. So this is going to be 0.250 minus x. And then this is just going to be plus x again and plus x again. Okay, so now we have our equilibrium expressions. Now we're going to set up our Ka expression and plug in the equilibrium expressions. Okay, so the Ka value for acetic acid is, let me look that up. Ka values. Okay, so the Ka value is 1.8 times 10 to the negative 5. And again, that's going to be equal to the product concentrations over the reactant concentrations. So again, it's going to be H3O plus concentration multiplied by the acetate ion concentration C2H3O2 minus all over the acid concentration C2H3O2. And now we just need to plug in the equilibrium expressions. So this is going to be equal to, again, x squared, since it's x times x, over 0.250 minus x. We'll do the x is too small again, so here we'll get rid of x to simplify. And again, we can do that, and it's a good assumption because this is here we have 10 to the negative 5. Here we have 2.5 times 10 to the negative 1. Again, it's a difference of a factor of 10 to the 4, right? So that's a large difference. So we solve for x. So again, I multiply both sides by 0.250. Square root both sides to get x. When we do that, we get x is equal to and 2.12. So x is equal to 2.12 times 10 to the negative 3. And so now we can find the percent ionization by taking x divided by the original concentration multiplied by 100. So we'll take this. So 2.12 times 10 to the negative 3 divided by 0.250 multiplied by 100. And that's going to be equal to, okay, so we get 0.85. You're going to get 0.8, what is it, 49%. So again, less than 1, less than 5. Since the percent ionization is less than 5%, the x is too small approximation is a good approximation. So this is how you would find the percent ionization of a weak acid. I hope this was helpful. If you like my videos, please like, share, subscribe, hit the notification bell, make a comment in the comment section. And thanks for joining me. I'll see you next time.